So, hello students, welcome to this lecture on the subject of advanced semiconductor devices KEC 056. This is lecture number 13. I am Dr. Raman Kapoor, Associate Professor at ABES Engineering College, Ghaziabad. In today's lecture, we are going to continue our discussion on PN junctions and we are going to study some more aspects associated with the operation of a PN junction. Okay. So, let us start today's lecture. In our previous two lectures based on PN junctions, we have covered all the electrostatics like electric field, built-in potential, depletion region width, and also how current varies when you apply a biasing to a PN junction. In the forward bias, there is lot of exponential current. In the reverse bias, there is constant reverse saturation current. The Shockley equation or the IV equation of diode can be written as I equal to I naught exponential of V over V t minus 1. Okay. So, this is your total current, this is the applied voltage. Okay. So, this is how you get the IV curve, this is your thermal voltage, okay, Kt by Q dependent on temperature, and this is known as reverse saturation current. Okay. This is the current, the only current which flows when the diode is reverse biased. So, this is how the graph looks like. So, if this is a V I, you get exponential current and you get constant current. Okay. Now, when we talk about breakdown, the name itself suggests that this is something which is undesirable. Okay. Most of the cases it is undesirable, but in some cases you can exploit this breakdown behavior for some applications. Okay. Whenever a sufficiently high electric field is applied, so you increase a lot of biasing applied to the diode, the junction can break down and it can conduct very large current. Okay. We know that a diode works like a switch. It is a closed switch in forward biased, it is an open switch in the reverse bias. So, if very large current is flowing, if it is flowing when the switch is closed, it is very good for us, because we want lot of current when a switch is closed. Okay. So, the concept of breakdown is only applicable whenever we are operating in the reverse bias regime. Whenever a reverse bias is applied, only then this concept of junction breakdown comes into play. Why? Because breakdown is associated with very large current. In the reverse bias, we want 0 to nothing current. Okay. So, this is undesirable during reverse bias only. So, whenever we say junction breakdown or diode breakdown or PN junction breakdown, we are referring to the reverse bias operation. Okay. There are basically three breakdown mechanisms. One is known as thermal instability. The word thermal basically indicates that this is something related to temperature. Tunneling, this concept we have studied in different forms earlier. Okay. So, instead of surmounting a barrier, if carriers are able to tunnel through or punch through the barrier, this phenomena is known as tunneling. Next is avalanche multiplication. Okay. This is quite a common occurrence of breakdown. Okay. So, we will discuss each breakdown mechanism one by one. Whenever we say thermal instability, the breakdown because of this is a major occurrence whenever there is the band gap is very small. Okay. What is energy band gap? This distance between EC and EV, this EG. Okay. If you keep on increasing temperature, you keep on providing more and more thermal energy. Okay. So, Boltzmann constant is fixed, Q is fixed. So, if you keep on increasing temperature, you keep on increasing thermal voltage or thermal energy. If this value of Eg is very small, this extra thermal energy may be possible, may be sufficient enough for electrons to make a transition from EV to EC. Whenever this transition happens, we say that excess carrier generation has happened. Okay. Whenever this happens, carriers become free to move. When they are free to move, they exchange energy that can further increase temperature, and that can further enhance thermal instability. Okay. So, due to the heat dissipation caused by reverse current at high reverse voltage, junction temperature can increase. Okay. If junction temperature increases, this further increases reverse current. The reverse saturation current basically doubles for every 10 degree centigrade rise in temperature. Okay. So, if temperature increases, reverse saturation current increases, movement of charge carriers increases, this further increases heat dissipation, temperature increases further, and more reverse current flows. Okay. So, this is sort of a positive feedback loop which eventually leads to a thermal induced breakdown. In some cases like BJTs, this is known as thermal runaway. Okay. And if we plot a graph, this graph is nothing but an IV characteristic. So, you have current density, reverse current density on y, and you have reverse voltage on the x. Okay. So, reverse voltage versus reverse current, just the absolute values, and the graph is being obtained at different temperatures. So, when you say that the temperature increases, this curve shifts more towards the left, which means current is increasing for a fixed voltage. Okay. And these horizontal line basically tells you a current density at a constant temperature, and which voltage, this is known as a turnover voltage VU. So, you can see that when temperature increases, right, you are getting more and more current being flowing whenever temperature is increasing, and if temperature is kept constant, you can say that the value of VU is being the value of current at turnover voltage is also changing. So, current at turnover voltage rises with increase in temperature. Okay. So, this is how the increase in temperature basically shows you what happens to the reverse current. Higher temperature, higher reverse current further increases temperature, and there is further increase in reverse current. Eventually, your reverse biased PN junction breaks down. This is thermal instability. Tunneling effect usually occurs, which is another type of mechanism of breakdown. This generally occurs when the junction is under a very large reverse bias. Okay. Now, all the junction breakdown mechanism occurs during reverse bias only. What is specifically different about tunneling is that you see this gap between EC and EF here, or EF and EV here. Okay. Just see this slope is quite steep. Okay. So, if I try to approximate the shape in the middle, the barrier which is being encountered is a triangular barrier. Okay. This barrier usually happens when there is lot of doping has been introduced on the P side as well as on the N side. Okay. We know that Xp by Xn is equal to Nd over Na. Suppose Na is constant and Nd is increased. Okay. In that case, Xp by Xn is going to increase, or I can say that Xn reduces. If this is kept constant and Na is increased, this ratio is going to reduce. I can say that Xp is reducing, which basically means, or if I increase both types of doping, Xp and Xn both are going to reduce to maintain the same ratio. This basically means that the width of the depletion region is very small whenever doping increases. Okay. This kind of a situation allows or assists the phenomena of tunneling, and the maximum height of this triangular barrier is basically equal to the energy gap only. In this case, instead of going through the barrier like this, so instead of electrons taking this steep barrier, these electrons can simply tunnel through, because this distance is quite small, this because of the steepness. This phenomena is known as tunneling. Almost always occurs whenever there are very high levels of doping in both P and N side of the junction. Okay. If the field, electric field, this field which I am referring to is the electric field across the depletion region. When this approaches say a value of 1 megavolt per centimeter in silicon, significant current starts to flow by band to band tunneling. What is band to band tunneling? Generation basically means carriers move from EV to EC. Instead of going through this barrier, if they go from one band to another, tunnel through, this is known as band to band tunneling. Okay. To obtain such a high electric field, okay, now I have said that when doping increases, this WD reduces. Okay. And when doping increases, another thing increases, which is built-in potential. Why? Your built-in potential is equal to thermal voltage natural log Na Nd by Ni square. When Na Nd increases, V naught increases. Depletion region width is proportional to square root of Na plus Nd divided by Na Nd. Okay. So, when Na and Nd increase, the product usually rises more as compared to the sum. So, Wd eventually reduces only. Okay. So, depletion region width reduces and built-in potential increases whenever doping is very high. Electric field, the peak electric field is given by this expression. So, V naught is increasing, Wd is reducing. Okay. So, numerator is increasing, denominator is reducing, which means that the peak electric field at the junction is very high. Okay. So, electric field across the depletion region rises very much whenever there is high doping on P and N side. This electric field helps your minority charge carrier, because you have your electric field direction is from N side to P side, positive donor ions to negative acceptor ions. This is very much useful or supporting for minority charge carriers. In reverse bias, current is because of minority charge carriers. So, high doping supports the phenomena of tunneling. Okay. Breakdown voltages are generally less than about 4 Eg by Q are due to tunneling effect. So, your level of voltage at which reverse voltage at which breakdown happens also reduces. Okay. For breakdown voltages higher than 6 Eg by Q, we are generally referring to avalanche multiplication. Okay. So, intermediate voltages between 4 Eg by Q and 6 Eg by Q, both mechanism can coexist, right. Energy band gap in silicon and gallium arsenide, one is elemental, another is compound. They decrease with increasing temperature. So, breakdown voltage in these semiconductors due to the tunneling effect has a negative temperature coefficient. Okay. So, the breakdown voltage decreases with increasing temperature. This is because a given breakdown current density Jt, okay, any breakdown current density, this is the current which flows when your diode has undergone breakdown. This can be reached at smaller reverse voltages or electric field at higher temperatures. Okay. The temperature effect is generally used to distinguish the tunneling mechanism from avalanche mechanism. Avalanche mechanism has a positive temperature coefficient, which means breakdown voltage increases with increasing temperature. Tunneling has a negative temperature coefficient, which means breakdown voltage decreases with increasing temperature. Okay. Lastly, the third mechanism of breakdown is known as avalanche multiplication. The word avalanche itself means something which takes increased proportions with time. Okay. So, it starts with something small and then it keeps multiplying itself into the form of an avalanche. This is generally happening via a mechanism of impact ionization. If an high energy electron is present inside the PN device, that high energy electron can knock off another atom and produces an electron hole pair. It transfers its energy to another free electron. That high energy electron can knock off another electron. So, this way one high speed electron can multiply the free electron concentration. This phenomena is known as impact ionization. Okay. There are certain examples like MESFETs, MOSFETs, impact devices. Okay. Some of these we are going to study in later lectures. This is where impact ionization mechanism can be used to generate high power. Okay. So, basically you can use also avalanche mechanism for certain useful cases also. Generally it is undesirable. Okay. The avalanche breakdown voltage is defined as the voltage where your MP approaches infinity. What is MP? It is defined as the multiplication factor and expressed as the ratio of total carrier concentration across the depletion region divided by the equilibrium concentration. Okay. So, total carrier concentration across the depletion region. Now, there is generation taking place. In the IV expression, we had assumed that there is no extra generation or recombination. Okay. But when you are trying to break down at high voltages, there can be certain generation. So, net concentration divided by equilibrium concentration is your multiplication factor. When this approaches infinity, that is where we say that avalanche breakdown has happened. Okay. The breakdown condition depends only on what is happening inside the depletion region and not on the carriers that actually started the avalanche process. Okay. So, that high energy electron which started producing more electron hole pairs, that just initiated the process of breakdown. Okay. Now, whatever is happening, generation is happening inside the depletion region, that basically decides whether avalanche breakdown has happened or not, right. So, avalanche breakdown for one sided abrupt junction, whenever we say one sided abrupt junction, we mean doping is very high on one side as compared to another side. So, wherever doping is low, most of the depletion region is on that side only. Okay. So, this is the breakdown voltage. E naught is the peak electric field, N is the doping on the higher side. Okay. Epsilon as E naught square by 2 q n. Avalanche breakdown voltage for linearly graded junction, okay, wherever there is a gradient in doping. So, from P to N we are moving via grading system. Okay. This is the level of, this is the equation for breakdown voltage. Epsilon S is relative permittivity of the semiconducting material, Q is Coulombic charge, E naught is the peak electric field, okay, and N here is basically the doping on the highest of either Na or Nd. Okay. The breakdown condition depends only on what is happening within the depletion region. As I have already said, it does not depend on the initiation of the process. Okay. So, beyond breakdown, although that is an undesirable effect, we know that there is something called transient behavior. Okay. This usually happens when you apply an AC signal, a small AC signal is applied across a PN junction. So, you will have positive half, negative half of the AC signal. Diode can fluctuate, switch between forward to reverse and reverse to forward. Okay. So, for AC application, we would say that since diode works as a switch, so whenever it is switching from forward to reverse or it is switching back from reverse to forward, we want such type of switching to be smooth and the transition to be very fast. Okay. From forward to reverse, generally the things are that when you are trying to turn something off, okay, it will be abrupt with very short time, but when you are trying to turn anything from off to on, okay, that is also we wanted to be swift. However, this transition from forward to reverse, okay, the transition from on to off is actually affected by how much charge which you have already injected. When you forward biased a diode, you injected charge carriers on either side. Because you injected charge carrier, they are still there, and all of a sudden when you change to reverse bias, that charge has to be removed, so that you switch from forward to reverse. Okay. That is generally usually a spot of an issue. Okay. So, the circuit which is shown on your screen basically tells you how the transient behavior can be studied. So, you have forward voltage positive connected to P, a reverse voltage negative connected to P. This is the forward bias circuit, this is your reverse biased circuit. Okay. Whenever P is connected to negative, N to positive, this is reverse bias, P to positive, N to negative, this is forward bias. You have a switch which can take one position at a time. So, here it is forward bias, here it is reverse bias. Okay. During forward bias, forward current IF flows, during reverse bias, reverse current IR flows. If at t equal to 0, we just throw the switch from this to here. So, here to here at t equal to 0 from forward to reverse. An initial reverse current flows given by IR equal to VR minus VF by R. The transient time is defined as the time in which the current drops to 10% of the initial reverse current IR. So, 10% of this, okay, and is equal to the sum of two time components T1 and T2. T1 is known as one particular phase which is constant current phase. So, if you see this IV characteristic, IR is approaching I naught, reverse saturation current. This is t equal to 0 when we switched from forward to reverse. Okay. So, from here initially there is constant current and then this current starts to decay. Okay. By the time you have reached 10% of this, okay, 0.1 10% of this initial current, that is the total transient time. Initially current is constant, that is known as T1, and then it starts to decay and that time it takes is known as T2. Okay. So, from 0 to T1 it is constant current phase, from T1 to T2 it is decay phase. Forward to reverse switching behavior, as I have said, can be separated into two phases. Switching from 0 to T1 is constant current phase. This time reverse current IR remains constant and the junction voltage Vj is given by thermal voltage Kt by Q, natural log of whole concentration on n side as a function of time divided by equilibrium concentration. Okay. So, net concentration which is a function of time divided by equilibrium concentration. It remains of the order of Kt by Q only Vt, okay, because this is very close to 1 initially. So, the natural log is a very small number, right, or a number which is generally closer to 1 only. So, well, of the order of Kt by Q only you are getting junction voltage. After T1, hole density starts to decrease below its equilibrium value P n naught. Okay. So, the junction value tends to reach the reverse voltage minus Vr and the current reaches saturation value. Okay. This is the time, the decay phase from T1 to T2 till it reaches 10% of its initial value. Okay. So, the distribution of minority carrier density and junction voltage is shown here. This is the minority carrier density holes on the n side with respect to distance starting from the depletion region width on the n side. Okay. When t equal to 0, this is the trend it shows. Between 0 to T1, this is the trend it shows, and at t equal to T1 this, and as t increases this concentration is reducing down. So, you are removing the injected minority charge carriers. Okay. Similarly, junction voltage, initially there is constant forward voltage around 0.7 volt for silicon, then from till about T1 it approaches 0. So, it is approaching the switching time. From there it increases in magnitude and approaches minus Vr. Okay. So, this term you can say is around T2. This is the transient behavior of a PN junction when you apply an AC signal across it. Okay. Finally, the concept of noise, well, as the name itself suggests, if it is noise it is undesirable. Okay. So, it refers to those spontaneous fluctuation in the current passing through or the voltage developed across semiconductor bulk materials or devices. Many semiconductor devices are used as amplifiers to amplify small signal or to measure small physical quantities. Spontaneous fluctuation in I and V, okay, can set a lower limit to the resolution and sensitivity of these devices. How small a signal it can sense, how small a signal it can amplify or measure. Okay. So, it is important to know the factors which contribute to these kind of limits, and this is where the analysis of noise comes into play. There is a very large dedicated field to just to study noise coming from PN junctions only. Okay. Noise generally classified into categories like thermal noise, also known as Johnson noise, flicker noise and short noise. Each are characterized separately. Thermal noise in any conductor or semiconductor device is caused by the random thermal motion of charge carriers, okay, because it is thermal. So, it is associated with some type of temperature fluctuation or thermal motion. It is also known as white noise because its level is same at all frequencies. Okay. So, generally frequency independent, the level remains same at all frequencies. For any open circuit, the mean square voltage of thermal noise. So, if you open circuit and see how much impact it is showing on the output, the mean square value of this noise is equal to 4 kBT B dot R. So, kB is Boltzmann constant, T is temperature, B is bandwidth in hertz and R is the real part of the dynamic impedance dV by di. This is dynamic impedance, it is going to be a complex number, the real part of it is used for this thermal noise. Flicker noise is distinguished by its peculiar spectral distribution, which is proportional to 1 by f to the power alpha, with alpha generally close to unity. So, this is also known as 1 by f noise. Flicker noise is important at lower frequency because of this dependency of 1 by f. So, f is low, 1 by f is very high. So, flicker noise generally dominates at small frequencies. Okay. For many semiconductor devices, the origin is the surface effect. 1 by f noise power spectrum can be correlated with the lossy part of the MIS, metal insulator semiconductor gate impedance, due to carrier recombination which are present via interface traps at the surface, the so called dangling bonds. Okay. Finally, short noise is due to directness or discreteness of charge carriers that contribute to current flow, and it constitutes major noise in many semiconductor devices. It is independent of frequency at low and intermediate frequency, but only dominates at higher frequency. This is the mean square noise current for short noise, which is equal to 2 q b I. I can either be forward or reverse current, we only need the magnitude. Okay. So, just for summarizing, these are your noise levels. Okay. This is your short noise. From diode equation you can get these values. So, you can get I in terms of R, and this is the value for the mean square current of short noise. Okay. So, it is dependent upon forward voltage, it is dependent upon reverse saturation current as well. These are the references which you can refer to. Okay. So, with this we come to the end of today's lecture. We have covered things like junction breakdown, transient analysis and noise in PN junction. Thank you.